All right, hello. So today we are going to look into the very first shortcuts for derivatives. Yeah, we're not going to spend the rest of the year using the limit definitions. Instead, we're going to sort of figure out why the limit definitions can lead us to some rules and properties here. But first, before we begin, let's talk about derivative notation. Because we have been using the f prime notation. So f prime of x or a or whatever, like your variable actually doesn't matter, but we tend to stick with x as our sort of variable of choice here. So that can be rewritten in some different ways using different notations. So this one's like been more recently adopted, and by recent I mean like in the last couple hundred years. But some of the first people to do derivatives use different things. So for instance, Leibniz liked using this notation here, d over dx of f of x. So that means the derivative. So this comes from thinking about like the slope formula. It becomes even more obvious when you sort of write it like this. df over dx, so change in f over change in x. Tiny changes though, so that's why it's the d. If the function were, for instance, called just y, you could do dy over dx. And then that was Leibniz wrote those ones. Newton had a different one. He did like, I think this one, like big D with a little x there, which we don't really actually use or see like ever. Maybe you might see it in some older textbooks, but for the most part, it's this notation we'll see here. So we're going to get into thinking about that notation to help us come up with some shortcut rules here. So let's start with these two here. So these two, what is the derivative of c if c is a constant? Well, I think the graph of this is what's the most helpful. If you graph a constant, like y equals 2, let's say, it's just a horizontal line. And then when you think about what a derivative is trying to tell us, which is the slope of your curve, the slope of a horizontal line is always 0. You could also prove that using the limit definition. So same sort of thing here. You can go ahead and think about, all right, that's just a linear function with a slope of 1. This is saying what is the slope of that function, so this will always be 1. Also provable using the limit definition. So those are good things to maybe just sort of do. They're pretty trivial, but it gives you an idea of like how proofs will work with regard to these rules here, because we will be proving some in class and some will be left to you on homeworks or tests. So, but these ones are so simple and short. I'd say like on your own time, just do them. Okay, so what else we got? Well, what if we wanted the derivative of c times a function, a constant times a function? Well, the way that works out is very similar to like limit laws. You can just pull out the c and then just take the derivative of the function, which we'll define as being f prime of x. So yeah, like the c you could just sort of ignore and just think about taking the derivative of f. Here, again, like limit laws make this pretty intuitive. The derivative of two functions added together is the derivative of the first function plus the derivative of the second function. This one here, I think you could probably guess it. Derivative of the first function subtracted by the derivative of the second function. And so those three there, this one has a name. It's called the constant multiple rule. This is the sum rule. This is the difference rule. The names aren't that important, but they come from using the limit definition of the derivative and then those limit laws. Like that's why they look very similar to the limit laws that we have seen. This one's a little bit different here. So this is a power function, x to some power. Your base has to be the variable x. or just any variable really, and your exponent has to be some number. So if you have that, then there's a rule that says that the derivative of x to the nth power is n times x to the n minus 1. That's called the power rule. And that one's special enough that I'll actually write down the name. The power rule. This is probably the one you'll end up using the most because there's a lot of stuff, especially in this first semester, that's going to be like polynomials and rationals, which are going to be a lot of x to the some power in them. So the reason behind this also can be found using the limit definition. You just need to know some other algebraic properties in order to be able to prove it. This one we will do in class together for sure, because it is interesting enough to sort of work through. But these ones I'd say you can do on your own pretty quickly, and then expect to see these in the future on homeworks and stuff like that. So the power rule is, like if you sort of just follow it out, it's like whatever your exponent was before is now the coefficient here. And then you still have the same base of x, and then you reduce your power by 1. You reduce your exponent by 1. So let's see some examples of using specifically sometimes this one, but then sort of all of them eventually. So here we go. We have find the derivative. So the first one we have here, that f of x is equal to x to the 6th. Okay, so we want to find the derivative f prime of x. And so this one is exactly of the form of the power rule here, x to some power. And so if I just follow along with the derivative rule, I get 6, that's my old exponents, times x to the, and then we're going to reduce the exponent by 1 to get me 5, 6x to the 5th. Cool. Over here, we got y equals x to the 1,000th. And so this is one of the first ones that you might be going like, oh, thank the math gods that I'm not using the limit definition, because that would not be fun to deal with in any of the limit definitions. All right, so this one, we're going to find the derivative. I'll call it dy over dx. You could also call it y prime. I didn't say that earlier up here. I could write that up here as well. Y prime is totally allowed as a notation, just FYI. So dy over dx is equal to, and so using that power rule, my coefficient will be 1,000, since that's the exponents on the original function, times x to the, and reduce that power by 1, 999. All right, number 3. Just because we have a t doesn't mean that the power rule doesn't come into play. It totally does. So it doesn't matter if this is x or t or a or whatever. So yeah, this time I'll use y prime. Y prime equals that coefficient 4 times t to the reduce it by 1 to the 3rd power. All right, next one. Next one you might be thinking, well, that one doesn't quite match any of these rules. You didn't tell us, like, how do you deal with division within a derivative here? And the thing is that this totally is one of these here. This can be rewritten as x to some power. So using our algebra knowledge, we know that this is equivalent to x to the -2nd power. So if we write it that way, now it becomes a little more obvious how we would find the derivative here. So f prime of x is equal to, so my exponent is -2, so that's my coefficient, times x to the, and then reduce by 1. Super common mistake is that you see the 2, you want to reduce by 1, so you write -1. But remember, that actually is adding 1, so we actually go to -3. -2 minus 1 is -3. And if you wanted to rewrite this in sort of the same form they gave it to you, you can. So this would be -2 over x cubed. And there's the derivative of that one. So this works on negative exponents as well. We won't prove that in class. We're only going to prove that this rule works for positive whole number exponents. But what we'll find out as we sort of move along is we'll get some tools that'll help us figure out like it totally does work for this, and it even works for like all real number exponents. So like if you have, you know, 6.5 as your exponent or pi as your exponent, it will work actually. So, all right. And then these last two. So these last two now, so those first four were just about basically using the power rule. So now we're going to get the other rules involved here. So here we want to take the derivative of this. So this one, it's saying like take the derivative of this expression. So like I don't have like an f prime or y prime to write down anywhere. So here we go. So this is going to make use of the constant multiple property here. So in other words, what this is saying is like that 3 down here, I can just bring out in front and not worry about it anymore and put all my focus into finding the derivative of f. So the derivative of x to the 4th. Well, that is now using the power rule again. So that will be 4 times x cubed. And so when I simplify it, I get 12x cubed. So yeah, so that uses, so that 3 we just sort of bring along for the ride since it's a multiple there. Again, that's fitting with the limit laws that we have. You can sort of just bring the 3 out in front. All right, over here now, we got a bunch of stuff added and subtracted together. Some of them got coefficients. So this is going to be a case where we're going to use this rule, this rule, this rule, this rule, and probably these rules as well, as I can see that there's going to be some constants and zeros or x's down there. So here we go. Let's go through this. The derivative of this is, so we're going to take it piece by piece. So these two rules here say, if you are adding and subtracting a bunch of things, you can just take it term by term, and that's exactly how my brain's going to think about it. So first one, 8x to the 7th is the derivative of that, plus, okay, that coefficient of 12 is coming along for the ride, since it's a multiple, times, and then take the derivative of x to the 5th, minus 4 is coming along for the ride, times, and then the derivative of x to the 4th is 4x cubed. I think I'm going to run out of room. Ruh-roh. Okay. So I'm going to jump down here for it. So plus, so then here, 10 coming along for the ride since it's a coefficient. Now I focus on x cubed. That is 3x squared is its derivative. Minus 6 is coming along for the ride. Derivative of x, that's a line with a slope of 1, so it's just 1. Plus constant 5, that's just a horizontal line which has a slope of 0. All right, so let me simplify this, and now I've got the derivative there. So 8x to the 7th plus 60x to the 4th, right? 12 times 5, 50 plus 10, yeah, okay. Minus 16x to the 3rd plus 30x squared minus 6. And you don't need to write the plus 0 because it's not necessary. Okay, so there you go. Quick sort of disclaimer here. Oftentimes, students sort of will see this and think like anything with an exponent can use the power rule. So let me give you a quick disclaimer. So something that seems like it could be a power but is not a power would be like 2 to the x. Because in your head you see like there's a base and there's an exponent. The difference between this and say this is where your variable is. So this x is the exponent here, 8 is your exponent. So this power rule depends on that your exponent is a constant and not a variable. So you cannot use the power rule here. So just keep that in mind as we move forward here. We're not going to see a ton of these this first semester, but in the second semester, if you see this, Your brain should not go to power rule. It is not a power function, it's an exponential function. Okay, thank you. Please take the survey, and we will talk about more of this in class.